All right. So our lesson today is based on applications of the cross product. So last day, what you guys were doing is you kind of learned what it was and how to perform the operation itself. Okay. So today we want to look specifically at a couple areas where the cross product is used. Okay. Much like the dot product, how we used it for work or the calculation of mechanical work, cross product has a couple applications as well. Okay. And as you spend more time doing post-secondary math, you'll probably see a lot more applications depending on how much math or physics you do. Okay. So one of the examples that we'll look at is something called torque. Okay, your handout should have a lot of this on there, but there are certain parts that are whited out. So as I click on my screen, you'll see certain words pop up. Okay, so you may have heard of the concept of torque, I don't know how long ago, right? It's just one of those words that seems to be a part of, I don't want to say everyday language, but you might have heard of that concept before. So it's just a force that acts on an object in order to rotate it. Okay, so that's really what torque is. The Greek letter tau. Okay, it looks like pi, but it's missing a leg. You know what I mean? It's pi without a leg, so that's tau representing torque. Okay. As far as the formula is concerned, okay, we're going to use the vector, or also known as the cross product. Okay, the vector product and the cross product are synonyms. Okay, and that will determine the torque, or another word for torque is the moment. So maybe through physics you've talked about moments. Okay, about the center of the object being rotated. Now, when I was prepping these handouts, what I did, I don't have my source on here right now, but not that I endorse all sites, but I did find this off. This is a Wikipedia graphic. You might notice that if you're doing a search on torque. And this diagram here, okay, I'm just going to reveal a few tidbits of information with regards to that. What you're going to notice in the diagram is that the torque really is a vector, okay? And that vector, okay, is going to be coming out of the page, okay, or out of my screen, centered from where you see that red dot, okay? The position vector r is really, if you want to call it the length of, say, the handle on a wrench, okay? Usually torque, we talk about, nuts and bolts and using wrenches to tighten things. It's also used with respect to, displacement in an engine. So the position vector can often be thought as the length of the handle to a wrench. Okay. Notice in purple we have a force. Okay. So this force F is applied to the object. Okay. But what you need to take note of is only the perpendicular component. Okay. So here's the symbol here for perpendicularity, right? It looks like an upside down T. Okay, for perpendicular. It's only that component which produces the torque. Okay, so to kind of get an appreciation for that, just gotta throw a quick question out to you. In terms of tightening things, like anybody handled a number of wrenches over the years, like in tightening stuff, anybody? Changing tires, anything of that nature? Okay, so you can kind of get a sense that based on where you're grabbing the wrench and how you're holding it, the angle to which you're applying the force, you very well know that certain angles or positions that you're holding it will produce an appropriate amount of force or torque to actually turn it loose or to tighten a screw. So the same thing happens here. If this vector here, if this truly was the vector that we were using to calculate torque, which is not, okay, you really wouldn't get much of a moment, right? You wouldn't get much force that's going to push or turn that screw in or out. So it's this vector here that's highlighted in blue that really is going to maximize or give you the torque that you need. Okay, so that's kind of important to take note of. The reason why we're using this vector also, or more importantly, is that we're going to have to use an angle, which will involve perhaps a sine or a cosine later on, okay, when we're calculating. Any questions so far with regards to the background information? Okay, well, let me pull this back into place here for now. There's also a right-handedness to torque. So if you can kind of picture trying to wrap the vector F around the vector R, okay, by using the right-hand rule, you're going to get a thumbs up, right? So we've got a thumbs up on that, meaning that this torque is going to have a vector coming out of the screen. So if you want to put that into context in terms of nuts and bolts and screws, really that screw is going to be coming back out. So you're loosening. Okay, so with the background info in place, what we'll do is we'll move forward and we'll take this formula here. Okay, so we're going to calculate the magnitude of a torque, and that's dependent upon a few things. Number one, it's dependent on the magnitude, really of the handle of the object that you're using, the length, the force F, and as well as the sine of the angle theta. Okay. Moving forward. So what we'll do at this point is we'll sketch things out, and I think I'll pause the video for maybe a couple of minutes, and that'll allow us to do the calculation. Okay, so let's take our time with this. I tried to be a little creative here in terms of making my diagram. So we'll go with the context of a wrench. Did I pause? Oh, we're going to let it run actually until we do the calculation. Yeah. Okay. So there we go. We've got a bolt that we're going to try to tighten into place. Just to emphasize what we're doing here, just to make it a little more fantastic here. So the one that's more transparent, of course, is, say, the initial position of where the wrench is. And then we really want to see that wrench being turned through, right? Turned through that particular angle to that position that's there. Okay. If you look back at the information, we have a force of 75 newtons being applied counterclockwise. So I've got my direction right? Counterclockwise. It's 12 centimeters from the center of the bolt. So that doesn't seem like a whole lot. In terms of a wrench, I'm trying to think of what that would look like. What would that be? Maybe a 7/16 wrench? Small wrench, maybe? Not sure. But at any rate, so what we have here, this vector here, okay, this is going to be the vector R in our case. We're going to draw a force vector, okay, that is at 60 degrees to vector R, okay, or the length of that handle. So the force vector, whatever color you want, let's bring that in. Maybe that looks about 60 degrees, possibly, okay. So we have this force acting this way here. That's our vector F. And we've got a 60-degree angle, okay. Okay, between vectors F and vectors R. And so our job is to calculate the torque based on the information that's given. Okay. So, as we were showing on the previous page, the magnitude of torque is nothing more than, it's actually a cross product. So if you remember back to the online module, one of the first things you might have seen for cross product is it gave you a definition where you took one vector and the other, you multiplied their magnitudes, and that was multiplied by the sine of the angle between the vectors you were given. Okay. Another thing to remember too is if we go back to this page here, according to this definition here, the torque is produced using the perpendicular force, or force perpendicular to that. So if we go back to what we're doing over here, it's really not F that's producing the torque, but it's F sine theta, or F sine 60. That's going to give us the force component that's perpendicular to, okay, to that vector r that we have there. So I'm going to pause the video here just to give you a chance to do the number crunching. This isn't a, we don't want to take up video time doing number crunching. So if I could have you make, okay, so you calculated the torque or the moment, right, as 7.8. So now we need to attach some units to that. Okay, so as far as units are concerned, we're going to use Newton meters. Okay. So Newton meters for torque. Notice that because it's in meters, okay, this did not come up in an earlier part of the video, but the meters is there given the fact that the original measurement was in centimeters. So just keep an eye out for that. And just because you don't end up with those units in a problem, you might end up with feet and pounds. Usually it's not an SI unit, but obviously in the States and even in a number of things you buy, you'll find foot-pounds of torque as being a unit of measure. Okay. Any questions at all about our example on torque? Okay, moving on. What else can we do with cross products? Well, maybe not quite as interesting as torque, but we can actually determine volumes. Yeah. Did I miss part B? Thanks for bringing that up. Sorry about that. Got a little ahead of myself. Part B. This one here, again, I apologize for that. Doesn't require a whole lot. There's no calculation involved, but by the right-hand rule. I'm just going to call right-hand rule RHR. Is that okay? Just to be brief. So by the right-hand rule, the torque or the moment, right? So we're talking about the vector tau. Into the page or out of the page, guys? Out? Exactly. So by the right-hand rule, tau is directed out. Okay. So if it's out of the page, then the bolt is moving counterclockwise. I'll just put CCW counterclockwise. All right, part B. We're good. So we're getting up around the 14-minute mark. We'll introduce the next one, and then we'll try to package our lesson in smaller pieces. That actually makes it a little more manageable in posting videos too. So as mentioned earlier, we can figure out the volume of particular solids, and this one here is called a parallelepiped. Say that 10 times fast. So more or less this shape, I'm not going to use the name again because I'm surely going to mess it up. I got it right the first time. I'm going to kind of stick with that. Um, but we have a sixth face solid, okay? And every side of the solid is a parallelogram. In this case, those sides, they're congruent, okay? So you could have a cube, of course, would be a rectangular prism. All sides are the same. This one here, all sides are the same. It's just that they're parallelograms. So our job is to find the volume of this particular prism, and it's the product of its base area and its height. So, and that goes for any prism, okay? Be it this, be it a cylinder, be it a a box of some kind, the formula is the same. Base area times height. Now we've actually already done base area through the online module. You might have seen or had been told that the cross product, its magnitude, is, let me just show these here, is the cross product of the two vectors, okay, that actually form, or from which you can form the parallelogram. So I'm going to draw in a couple vectors. Let's just call them A and B, if you will. So A and B, we'll just take A to be this one here, and we'll take B to be the other one here. It's kind of in the XY plane, you can kind of see A, and that'll be vector B. So from the online piece, or from what you might have seen from your textbook, we can see that the area of the base, we'll call it A, is the magnitude of the cross product. Okay, so half the battle's done. We've got the base area, or we know how to find it, because we can do cross products, and then we can find magnitudes of vectors. We've got that down. The only thing we need is the height. Okay? So here's what I'm wondering, is how can we use another vector? Notice that along the xy plane, we've only got A and B being used. Well, we could very well then use another vector, couldn't we? Or maybe at least try to use a different vector. Let's call this C. So I'm wondering, how can we use C to help us get the height of this particular prism? If you think in terms of a picture, any suggestions as to just going to dissect this a little bit, because if I start overlaying stuff, actually maybe I can. Maybe it's large enough here for my smartboard, but maybe on your page it might get a little messy. What if I were to, right? The height is simply the distance from this face on the bottom to the one that's on top. So what if we denoted this as our height, okay, and we form a right angle triangle right here? Can you sort of see that, sort of appreciate that we could drop a height down perpendicular to the base, and then start thinking about vector C and the height, and somehow they're connected. Okay? And moreover, if we're dealing with triangles, then obviously maybe some angles will get pulled into play. So between vector C and the height, we could perhaps use an angle of some kind. Okay, call it theta, call it whatever you want. I'm going to stay away from theta because we usually use that in other formulas. So I'm just going to go with, I think our textbook uses alpha, so I'll stick with alpha. Now, I didn't keep to my promise about the 15-minute video. We're right into it. We're just going to go. We'll see if we can't, we'll shoot for 25. Well, based on what's drawn, right, if you see H, vector C, and the angle alpha, I think the height could we not see that as the magnitude of a component vector? Like if we did the component to C, one of them, right? Every vector in 2 space has 2 components. We could, get the height. So let's figure this out. So under the formula area, we're going to do a little work to sort of come up with something together. I'm just going to pull that up a little bit more, give myself some space. So I'm wondering here, height. How should we combine vector C and alpha to come up with the height? What do you think? What about this? Maybe we could start differently. What if we did a ratio? Let's do that. If we did a ratio of the height to the magnitude of vector C. Let me move that equal sign down. Think in trigonometry terms. Yeah. Cos alpha. Any seconds on? Right? Adjacent side over the hypotenuse, cosine of alpha. Seems okay? Well, that relationship, that's true. And given that, we can find the height, right? Or a generalization for the height. So this relationship here, that implies that the height is going to be the magnitude of C times the cosine of alpha. So we've got everything actually that we need. Okay, we can move forward on this. The volume of any prism, again, is the base area times the prism's height. And because we have all of these elements, the area is the cross product of A and B. And then the height has just been given as the magnitude of C times the cosine of alpha. So if we left it here, that would be okay. We have a formula now for the volume of a parallelepiped. That's good, I said it twice correctly. 3 times the charm, I bet. But there's actually one more level to this, as if there couldn't be more, right? There's always something more. But dot product actually comes back. I know it seems kind of weird, right? We're doing cross product, Mr. Stewart. We're doing vector product. Why are you telling me dot product? Well, think back, okay? Recall a time not that long ago when we said that, or came up with, or whatever you want to call it, that I'm going to use 2 different vectors here. Remember the generalization u dot v? We said, or you said, I said, was the magnitude of u times the magnitude of v times the cosine of, I think it was theta at the time, right? We were using. Do you notice any similarities between the definitions? Kind of interesting, right? Like, why don't we just identify some like parts? So let's say that the u is this, right? U is a vector, A cross B is a vector, okay? And then, of course, the C and the V, you could match those up too. And then the cosines, they kind of match up as well, right? It's all the same now. So we've got these like parts. So that actually is going to allow us to rewrite this in another way, okay? So what that means, what does this imply? Well, the volume, right? It's a magnitude, but it's the magnitude of something quite miraculous here. It is the magnitude of A cross B but not cross C dot C. So we're actually using a cross product and a dot product to come up with the volume. Okay, and this is referred to as the triple scalar product. Triple scalar. You can see the triple part come out from having the three vectors. And then the scalar portion will come up in the work that you do in the next example. So we're going to shut the video down here, unless there's any questions that anybody would like to ask. Going once, twice, okay, sold. So we'll stop this part here and we'll pick it up again in a moment.